All right, now that we have defined our motion quantities, position, displacement, velocity, acceleration, we're now going to explore motion, and we're going to first explore motion with constant acceleration. And if we have a constant acceleration, then that means the instantaneous acceleration and the average acceleration are the same thing. They're whatever that constant value is. Just a quick note, the book conventions that are adopted, some of which I will use and some which I won't. The ones that I will use, delta t, which is defined as the final minus initial, the book adopts the convention that the initial time is 0. So delta t is really just t final, and then we're just going to adopt t for that time rather than calling it t final. Recall delta x is x final minus x initial. We're going to do the same thing with x. Instead of x final, we're going to call it x. Same with velocity. Remember, delta v is v final minus v initial. Instead of v final, we're going to use v. All right, so those are 3 conventions that we're going to adopt for the next few portions of the video. I'll point out that since we're going to work in 1 dimension, at first, the book drops the vector notation and the vector format for the kinematic equations in 1D. I'm not going to do that. I'm going to try to keep the vector notation around as long as possible to sort of emphasize that all of these quantities are vector quantities. But the book is going to sort of drop the vector notation. So keep that in mind. All right, so let's get started. Let's derive some of our kinematic equations. So first, we're going to start with the definition of average velocity. Remember, that's the displacement divided by the time. And remember, we just adopted the convention that delta t is just t, and that delta x is x minus x naught. So if I plug this in for delta x, t in for delta t, rearrange, this is a kinematic equation. This tells us how the position of an object changes with time. All right, so right here, one of our first kinematic equations. It's slightly limited in its use or application because it requires you to know the average velocity. Now, remember the average velocity defined here, the average velocity can also be written as the final velocity plus the initial velocity divided by 2. It can be written this way because the acceleration is constant. And so this is sort of what you think of when you think of the average, right? You add up the quantities and you divide by 2. So again, you can do that because we're dealing with constant acceleration. So this will come in handy in just a second. All right, next, let's recall the definition for average acceleration, which, since the acceleration is constant, that's the same thing as the instantaneous acceleration. That's the change in the velocity divided by the change in the time. So we're going to substitute t in, we're going to substitute v minus v naught, and we're going to end up with this kinematic equation. So the time-dependent velocity equation. So the velocity of an object at any time, you need to, if you want to determine that, you need to know the initial velocity of the object, and you need to know the acceleration, and then for how long the object's been accelerating. Now, if we add v naught to both sides, well, if we do that, this would become 2v naught, and this would be v naught plus v. And then we divide both sides by 2. Then I get this over here, v plus v naught over 2, and then v naught plus 1/2 at. So the reason I did that was to show, oh, this is actually the average velocity. And so the average velocity is equal to v naught plus 1/2 at. Now, why did I want to do that? Well, I am going to take this and I'm going to plug it back into this initial expression that I had written down for x. So I'm going to plug in the average velocity, and when I do that, I get this expression for the position. Again, it's an equivalent expression. It's just now, rather than needing to know the average velocity, I need to know the initial velocity and the acceleration. And so this is, along with this expression, the common kinematic equations that you will use to solve pretty much every one of your motion problems. I say pretty much every one because you'll notice that these equations both have time in it. So these are time-dependent expressions. And so it turns out what you can do is if you combine these two expressions, you can eliminate time and you can come up with a third expression, which is time independent. And so when we combine these two, we end up with this expression for a third kinematic equation. And the way the book presents this, v squared equals v naught squared plus 2a and then multiplied by x minus x naught, or delta x. And so I'm just pointing out up here that really this is the magnitude of v squared. This is really the magnitude of v naught squared. And really what's going on here is a dot product, because they are vector quantities. But in one dimension, the dot product basically turns into what you think of as traditional multiplication. And so these three expressions are the three kinematic equations that we're going to use to solve pretty much every motion problem in this course. So here I've got just a cutout from the textbook highlighting, they've got 5 different expressions highlighted here. Really, this expression and this expression are the same. The only difference is that v naught has been plugged in, or average velocity has been plugged in. So these 3 are really the kinematic equations you'll be using. On occasion, you might find it useful to use these first 2. Remember here, these are really vector quantities and vector equations, so you'll need to be careful and you'll need to pay attention to the vector nature of position or velocity or acceleration. In one dimension, that vector nature essentially gets described using the algebraic signs plus and minus, right? But it's really important that we emphasize, even if we aren't using the vector notation, that we're dealing with vectors and those plus and minus signs mean something. All right. One particular type of motion that gets pointed out in the book and emphasized, and we have experience with quite often in our daily lives, is something known as free fall. And free fall occurs when an object's motion is entirely influenced by the force of gravity. It's kind of tough to introduce this because we haven't actually talked about forces yet. That's coming in future chapters. But just know the acceleration of an object in free fall is entirely determined by gravity. And so here I've got this wonderful drawing. I'm holding a ball. I release the ball, and the ball accelerates downwards towards the center of the earth. And that's a result of the force of gravity. So on or near the surface of the earth, the acceleration due to gravity, so free fall acceleration, is 9.81 meters per second squared. That's the magnitude of the acceleration. And acceleration is a vector, so we need a direction. The direction is, well, typically we would say down, but towards the center of the earth. That's the acceleration direction in free fall. So if we adopt the convention that down is the negative direction, or the negative y direction, then typically you'll describe the acceleration due to gravity as minus 9.81 meter per second squared. That is only the case when down is your negative y direction. So this acceleration due to gravity is used all the time, and so we actually have a symbol set aside for it. Little g is the magnitude of the acceleration of an object near the surface of the earth, so 9.81 meter per second squared. So let's just make sure that we're clear on what we're saying. If my coordinate system plus y is in the up direction, then the acceleration of an object in free fall is magnitude 9.81 meter per second squared, but in the negative j hat direction, right? Up is positive j hat, so down is the negative j hat direction. That means if you were using little g, then the acceleration due to gravity would be minus g in the j hat direction. So what that means is that when we have motion, an object in motion in free fall, then our kinematic equations that we've written out, we can rewrite them assuming that we have adopted plus as the up direction and minus as the down y direction. So this convention right here, plus and minus. With that convention, then our kinematic equations, and typically we use the y variable for vertical motion, then our kinematic equations turn into, well, the acceleration just turns into minus g. The acceleration turns into minus g, and the acceleration here turns into minus g. And so those are our kinematic equations. Turns out those three tools will allow us to solve all of our motion problems in this course.